The intermediate value theorem is, well, it's very mathy in how it's worded. The concept behind it is actually relatively simple, but it does require some explanation. Not the kind of thing that I could fit into a PowerPoint slide. Much like the finding limits by graphing, it has to be demonstrated. It's a very visual kind of thing. So let's start with the clauses. Let f be continuous on an interval from a to b. So we've got a section of the x-axis somewhere. Could be anywhere. Just to make life easier, I'm going to kind of isolate the first quadrant here. So somewhere along the line we've got a value a, and somewhere we've got a value b to the right of it. The function is now continuous on this interval. That means that at any x value in this interval, here, or here, or here, or here, or here, or anywhere else, the function is defined. There is an output value. And the limit exists and matches the output value. So remember, finding limits, when we're looking at a graph, in order for the limit to exist, you have to be able to trace the graph of the function from both sides and have it meet up at the same point. And to be continuous then, there has to be an actual point of the function there. So no holes, no asymptotes, no jumps. So at the left end point somewhere, there's a point, and it has a y value. Since we don't have the specific function or the specific value of a, the best we can say is that the output value there is f of a. Likewise, on the right side, there's a point that we can say has a y value, f of b. Now, w is a value between f of a and f of b. W can be any value in here. W could be here. W could be here. W could be here. W could be literally any value in between them. So, I'm just going to pick this one at random. This dashed line represents every possible y value of w. Every point in existence that has a y value of w. Here's the trick. If you're going to draw a continuous graph, that means you have to get from this point here, a comma f of a, to this point here, b comma f of b, without any holes, without any asymptotes, without any jumps. Another way to phrase that might be to say that you kind of have to connect the points without ever picking your pencil up off the page. That's something that discontinuities have in common. Every one of them, the function goes somewhere and then has to pick up and relocate to a brand new spot, even if it's only skipping over a single little hole. If there's no discontinuities, then we never get to do that. We never get to stop in one place and then pick up somewhere else. So if I have to connect these 2 points, no matter how I do it, whether I use a straight line or whether I use something parabolic or polynomial in nature, even if it goes in a piecewise manner, no matter what, somewhere, even if it's more than once, somewhere I have to cross that dashed line. Somewhere I have to cross it. Discontinuities would allow us to break this. In its most simple form, if I were to allow for discontinuities, in its simplest form, I could just simply put a hole wherever I would otherwise be crossing that line. Discontinuity means I don't actually have to achieve that y value. Any other discontinuity is very much the same, and asymptote is also fairly straightforward. If this side goes down and this side starts at the top and comes down, again, I never have to cross that y value. And I think the most obvious should be a jump discontinuity, where I can literally just jump over. I can have anything I want that goes up, stops in one spot, picks up somewhere else, and I never have to touch that y value. So discontinuities would allow us to get from one y value to the next without hitting the y values in between. That is the nature of the intermediate value theorem, to say that if the function is continuous, that means it will use every x value in between, and it will use every single y value in between. That, when it's phrased like that, might seem a little bit obvious, a little bit kind of like a, okay, yeah, that makes sense, whoop-de-doo. It's actually an incredibly useful characteristic that, as I said in the PowerPoint, will pave the way for us to do much more important things later on. The idea that if a function is continuous on an interval, it must use every input value in the interval, and it must achieve every output value in between the two output values at the endpoints. Now, can it, as I drew here, extend beyond, below f of a, or above f of b? Absolutely. But there's no guarantee. What is guaranteed is that no matter where I draw that w, the graph has to cross the horizontal line at w. It has to achieve that y value at some point. One of the consequences of this is something called the bisection method. Actually, one of the things that your graphing calculator can do is it can find the x-intercepts of a graph. And if you've ever done this, you might wonder, how does it actually find the exact x value? What it uses is a algorithm that is based on something called the bisection method. So, for example, we have a function that is continuous on an interval from a to b. And on one side, the output value is positive. On the other side, the output value is negative. If the function is continuous, then it has to hit every y value in between here, including y equals 0. That means the only way to connect these 2 points with a continuous function is you have to cross the x-axis at least one time. Now, of course, the question might be, where exactly is that point? And this is what the calculator might do. For those of you who have done this method on the calculator, you need to tell when you choose to do it, you need to tell the calculator 3 bits of information. Only the first 2 are really relevant. You need to tell it the left bound and the right bound. The left bound identifies the left side of the interval, and the right bound identifies the right side of the interval. Once it has those 2 values, that's all the calculator needs to find the x-intercept. Of course, the process we're going to do is going to seem very slow because I'm explaining it. The calculator, of course, will do it very quickly. What I'm going to do is I'm going to come up here and I'm going to subscript this as a sub 0 and b sub 0. What the calculator then does is it finds the halfway point. Let's see, there are 16, so it finds the halfway point, the midsection. It literally bisects the interval a to b. And what it says then is it tests the output value at the midpoint. And what we've got here now is two separate sections of the graph. One section to the left and a separate section to the right. Now, one of these is actually a similar situation to what we began with. When we began, we had one endpoint above the x-axis, positive, and one endpoint below the x-axis, negative. In this case, the left side here, the left half of this interval, has that same characteristic, and that is where the x-intercept is. Because, again, we go from above the x-axis to below the x-axis. Somewhere in between, we must have crossed it. Note that on the other side, this is not true. We start below the x-axis, and we finish below the x-axis. If you start below it and end below it, there's no guarantee you've ever crossed it. And what we can see here is that it actually doesn't cross. So, what the bisection method does is it says, okay, we don't need the full interval a sub 0 to b sub 0. We've decided that this is the interval in question. So what it does is it throws out the right endpoint b sub 0 and redefines an interval, a smaller interval. We'll call this b sub 1. So we can now have a sub 0, or a sub 0 to b sub 1, where a sub 0 is, or has a y coordinate up here, and b sub 1 has a y coordinate down here. Excuse me, I should probably have marked that above the axis. Now, what it does is it repeats the procedure. We're going to, again, subdivide the interval. There is a point on the graph at that midpoint of the interval. And what we have here is, again, we've now separated this into two separate intervals, one on the left and one on the right. The interval on the left starts above the x-axis and ends above the x-axis. If you start above and end above, there's no guarantee you've ever crossed it, as we can see. But the left side starts above the axis and ends below the axis. What we get then is this side really is not important to what we need anymore. So we're going to throw out the left endpoint and slide it inward. We now have a smaller section. And what we get here is the same effect as a limit. We're slowly going to close in one at a time the left and right endpoints until we narrow it down so much that the left and right endpoints are actually approaching the same value. We get an interval that's so unbelievably narrow that it actually eventually could be said to only encompass a single x value. And that is where the x-intercept would be. Now, this is hard to illustrate as we go here, much like what we saw with the perspective on finding limits. It would require us to be able to draw this. It would require us to pull this and zoom it out to a wider picture. And I'm not working with a specific function at the moment. I just drew something. So, again, there are examples of this in the slideshow, and then in the homework there is practice with it. But the idea is that this gives us an idea of where the intermediate value theorem even has use. And I always like to explain this because it's kind of neat when you do something on a calculator and you give it this information that almost seems random. How is it actually coming up with its answer? Well, this is essentially what the calculator is doing. It does it very, very quickly. for those of you guys who have a background in coding and computer programming, you might actually recognize the algorithm a little bit. It's not unlike some of the sorting algorithms that they have you practice with in introductory programming courses. The algorithm itself is actually very simple. For those of you who know coding, this is about a 7 or 8 line for loop. Actually, I suppose this would probably be a while loop. But in any case, it's a very simple and short bit of code. You could, if you know what you're doing, you could write it yourself in about 10 or 15 minutes, maybe half an hour total, counting debugging. It's a very simple algorithm. It just is, of course, time-consuming to do it by hand, which is why we often use the calculator.